All right. Hi, my name is Jeff Flowers. I'll be going through some transactions. We'll also actually create a transaction using Node. Walk through that process. We'll fund it. We'll see how to then perhaps move that transaction to another address later. So we'll see the two. So I think what we'll do is we'll go through the PowerPoint right now, but then we'll actually work our way through it. Now, when Brian X. Charles talks about this, he'll go into a lot more detail, I think, about how this goes. So this is a very light overview of how it all works, just for transactions. We'll see how to roll our own and make our own transaction. So this is, again, how value moves across the network. So in this, we'll talk about transactions in general. We'll talk about their structure. We'll talk about the standard types. And we'll also talk about how I approached understanding a transaction. And then we'll do a couple detailed examples, and then we'll work some examples using Node and making our own. So again, a transaction can really be thought about moving control, I like that idea, moving control of an unspent transaction output across the network. So it's basically how value is transferred throughout the network. In fact, you don't own the coins, as we've learned, or rather we own just the ability to move that value unit across. And in fact, that's something important, I think. Bitcoin really is the ability to move value. And value doesn't have to be just currency. It could be anything. A fleeting moment, a kiss. These are anything that can be quantifiable. I don't know if they can be quantifiable, but anything that can be quantifiable can be moved around using this technology. And we're going to see that these transactions or these constructs are wrapped within a transaction and then pushed or broadcast onto the network. We'll see these transactions are, of course, clear text. We learned a little bit about all the cryptography that goes behind this, but these are, in fact, just plain text out on the network. Anyone can view it. And that's how blockchain explorers exist. They allow us then to see what's going on, how this value is being transmitted throughout. And we'll talk about, again, how these transactions move across the network. And we kind of saw that with the idea of relay nodes, full nodes, and of course miners. So again, all these transactions, every node, every miner, everyone connected to the network is validating transactions as they come across them and then pushing them to the other computers, other nodes that they see. So we'll talk about, let's see, what's the structure look like of one of these transactions. This is one of the important things, just to wrap one's mind around, that you'll see a lot about later today in the afternoon about data structures. And in fact, this was one of the main things I always had a problem with, was data typing and knowing, oh, this is a flow this long, and knowing how to do it. You'll see that later. I'm not going to go into his too detailed for the time being. So a transaction can be really thought about inputs and outputs, encumbrances and payments, or however you want to think about it. It's as you would expect, ins and outs. So inputs are the source of funds being moved. This is the Bitcoin that you control, the value. And you're going to use pointers to transaction hashes, sequence numbers of these unspent transaction outputs. Now, this is an interesting term that you really ought to burn into your mind. I like the idea that hashes, you got to just know what that word means, in and out. UXOs are also, this is Bitcoin, in fact. When you talk about Bitcoin, people are probably referring to unspent transaction outputs. This is what you're able to move across. This is what's kept in the mempool at all times. This is what people think about when they think about transactions or value being moved across the network between participants. So in the output transaction is basically, the output is a transaction which is a creation of this unspent transaction output. And the unspent transaction outputs, this is something interesting, they're always denominated in Satoshi. So Bitcoins are infinitely divisible, but currently they're divisible to 8 decimal places. That's a big sticking point to a lot of people when you talk about it going to be a deflationary currency or whatnot. They fail to realize that it's a computer construct, and you could have infinite divisibility. We just go to 8 decimal places currently. So, and the 8th decimal place is denominated as a Satoshi, so 10 to the minus 8.
Although to be clear, it wouldn't go beyond 8. Require a hard fork.
It would require a hard fork, yeah. I mean, and maybe it is impossible now. We've learned that it's really quite hard to change the block size. So, but
there'd be less controversy around that, right? I mean,
you would hope, but I mean, any time anything gets changed, there's controversy.
yeah.
Maybe somebody would say, I like 8. I don't like, 9. Maybe I don't know. But so when you're creating these transactions, you have to think in terms of Satoshis, which is counterintuitive since we always talk about bitcoins or millibits. We now need to think in terms of Satoshis. So we're going to have to move that decimal place over a bunch of places. And we're going to see that this transaction is going to have, if you will, a locking script that will encumber the funds. And they're going to require a specific set of conditions, which we'll learn about, I think, next week, of course, when we talk about scripts. And we're going to see how this specific set of conditions that are necessary to unlock will be in, a stack-based scripting language that will unencumber, let you spend the funds. So what is a transaction structure? What do you have to think about when you're talking about transactions? A transaction will have to completely deplete the unspent transaction output that's being used. So, can I use these?
Yeah, that actually goes on the walls over there.
Oh, even better.
Yeah.
So, actually, I like this idea. Perfect. So, if you have, let's say, Bob and Alice, and the idea is you want to pay Bob and Alice a certain amount. Bob wants to pay Alice a certain amount, and let's say it is, I don't know, $100. And Bob here has within his wallet various unspent transaction outputs, and we'll just call them, we'll just label them 0 and 1. And this one has 0.25, and this one has 1.5 Bitcoin, BTC. So I got through talking about Satoshis, but unfortunately I'm using Bitcoin myself. Well, if Bob needs to pay Alice $100, and inside the wallet that Bob controls, we only have these unspent transaction outputs totaling a quarter of a Bitcoin, which currently is how much? It's 225 now, I think, a Bitcoin.
Yeah.
So how much is that? I'm going to go with Chris.
$55.
And then at 1.5, that's what, $400? Well, neither one of these would, of course, be sufficient to pay Alice. This one is shy, this one's a bit too much. So if Bob's wallet software were to use this unspent transaction output labeled in the series 1, the entire amount has to be transferred over to Alice, the 1.5 Bitcoin. You can't send just a fraction of that. You have to send the entire amount. And of course, that requires this idea of change. So when we're looking at the transaction outputs on Block Explorer, we'll see that the various inputs or outputs will be the entire amount, and we'll have to send back change. So that's something to consider when you're doing it yourself. If you think, oh, I'll just send this amount and then a fraction of this amount, you might end up losing a lot of the value.
Has that happened before?
And that does. And that's why you should always use Testnet. So we'll actually get some Testnet coins today too, so we don't have that fear of loss.
I have a question. Is there a reason the wallet doesn't do it?
Oh, the wallet does do it. I'm thinking if you do yourself, if you roll your own, if you do it all by hand. But yes, that's the whole point of why you use a wallet. It would calculate this and figure out the best way. In fact, they optimize. There are many white papers out there talking about how to optimize the smaller amounts to give you the best possible transaction.
No, I'm asking the wallet computes. The wallet takes 1.5 Bitcoins, gives it to Alice, and then.
Oh yeah. So the question is, does a wallet do the transfer of funds? So the wallet would calculate. You want to send Alice a fraction of one of these amounts. In the case of the 1.5 Bitcoin, you want to send Alice, it looks like a quarter of that. So it would send the 1.5 Bitcoin and create a change address back to you. So it generated a new address with which the transaction would then redirect part of that change back to your control.
Why? Why doesn't the wallet send Bob and whatever the amount that it has to send Alice, and then whatever changes the other transaction and split that transaction that way so that it can send Alice only 100? There's no need that Alice is not.
Oh, I'm so sorry. Although I made it look like Alice is then redirecting it,
Right.
you could think of it as in terms of the entire amount is like that.
Okay.
Yeah. That makes it a little bit easier.
What's that? The entire amount?
So your wallet software would create the transaction using this unspent transaction output that you have control, Bob has control over. Send Alice the proper amount, and maybe let's say it's 0.25. And it would then create a new transaction back to Bob as the change.
Okay, so the wallet does that.
Yeah, the wallet would do all this. So that otherwise,
Alice is not sending back any.
so Alice isn't actually redirecting the money back.
But it's one transaction.
But it's one
It
transaction.
just has two outputs.
So two outputs. Yeah. Sorry about that. That'd be a little bit more cumbersome to do that, and you'd have to have a little trust. And hopefully we've learned that this whole network is based on, you don't need trust. So yes, so when you're rolling your own, you got to consider change. And that's why, of course, using the testnet is so critical, particularly when prototyping. I'll tell you some tricks about the testnet. You actually don't have to pay a miner's fee, one. You also don't have to wait the 10 minutes. Although, depending upon how you use it, it probably will enforce the 10-minute rule. So when you're making transactions, it's actually useful to have multiple, if you will, addresses that have testnet coins in them, and we'll talk about that and do that, so that you can then try it out and not have to wait the 10 minutes. But what else can we talk about with the testnet? Yes?
Quick question for the outputs will also have the minus fee embedded.
Yes. See, I actually, so the question is, hey, where is the miner's fee already embedded in that? And it's not in the actual data structure, but rather it's inferred by the data structure, in which the if you will, the inputs and the outputs, the difference is the miner's fee.
And
So again, the wallet would calculate that depending upon, if you will, the software, and whether or not you want your transaction to get into a block very quickly, or you don't care so much.
so the miners have a mechanism to sort the blocks to figure out the highest transaction fee and process that first.
So the question is, do miners have the ability to weed out transactions or to order transactions based upon miner's fee? And in the recent stress test, it would appear so, that is something that is frowned upon. However, about a week ago, there was a concerted effort to try to stress the Bitcoin network to see how it behaves. And sure enough, it would look like those with a minimum set, they didn't optimize based on the maximum transaction fees, but they did look for transactions with the transaction fees. Those were processed a little bit faster. And those without a fee took considerably longer. So I think you're going to see more and more of that. Now, the actual transaction fee schedule is a somewhat complex algorithm. So it depends upon, if you will, the size of the transaction or how big the data structure is itself. So in addition to what you're doing with it, the complexity factors into the cost. And that's why there's a lot of research involved in how to optimize the transactions to minimize its size, to have the minimal fee structure. Is if you had, if you will, thousands of these small unspent transaction outputs and you're pulling them all to pay Alice, it could lead to a larger transaction size that you then have to pay.
On that, so my understanding was that the transaction fee is there to prevent a denial of service attack, partly.
Yeah.
But does that not mean the testnet is open to that specific attack if you don't have to pay transaction fee?
So the question is, so if the testnet doesn't have or it doesn't enforce the fee, isn't it open to certain attacks? And although, yes, I imagine you could say that. And there was actually, in the last cohort, I couldn't even do a testnet transaction. There were problems with, if you will, the testnet being overwhelmed with hashing power. So the difficulty, because it takes 2 weeks for it to retarget, was off, and it was causing the testnet not to behave properly. Because everyone, I guess, was taking their miners that they had purchased for the Bitcoin, said, oh, I can't make any money there, and threw it onto the testnet, which caused the difficulty to spike very quickly, causing the entire testnet to become basically rendered unusable for a while. Actually, that was quite depressing, because we were talking about that first week of second cohort, and the testnet wasn't sending transactions, but that's, I think, has been fixed.
But to make sure I understand right, so let's say, in this example, let's say Bob's sending 0.25 Bitcoins to Alice, and let's say he wants to include a 0.01 transaction.
Yeah.
And so he's sending back change of 1.24 to his own wallet under his own control, an address under his own control. And then does the miner who finds the winning block actually include an additional
They
input?
benefit from any screw-ups.
Yeah.
So if you are off by a decimal
Gotcha.
point,
Yeah.
they're gonna take the decimal.
To that end, though, because, and that does happen when people, again, roll their own and do their own transactions, they oftentimes forget this, or they make a mistake and they send their entire, if you will, wallet, what they have in control, not realizing that. And yes, they can send all of their Bitcoin as a fee, or that does happen quite a lot, actually. It happened just recently I saw on Reddit, but you can always find out certain miners are better than others, that if they win the block and they have your transaction and they realize that you made a mistake with the fee, they will refund it. Now, of course, you have to wait. People don't mention this, but miners themselves don't get their Coinbase transaction or their profit, if you will, until 100 blocks. So you're going to be waiting until 100 blocks later. And you also have to hope that they recognize and they feel comfortable sending you back your value, your money. So it's best just to use software. But it's fun to roll your own and make your own software.
So the miner that wins the block gets the Bitcoin prize as well as all the transaction fees.
All the fees within that, yeah. So that's why they have an incentive to put transactions in.
So, but on the Bitcoin network, you don't have to pay transaction fees.
On the testnet network.
On the Bitcoin network, everyone has to pay a transaction fee.
You don't. Okay, so the question is, on the Bitcoin network, do you have to pay a transaction fee? And the answer is no. You don't actually have to. You just will be waiting a while. So if you're comfortable waiting, it's perfectly fine.
In long term, it probably. So what happens is that there's debate as far as the metaphors, but the reason why I like to use the Tetris metaphor is that miners can change that nonce that we were talking about yesterday. The other thing they can do is they can reorder the transactions that they've got, and sometimes they're just like desperate for something to fit. Because remember, it's it's 2K. What's the size of the transaction size now?
So I think it's the set prices for the first. Oh my goodness, I have it on the next.
Anyhow, they
Go to
may
the next.
juggle and put other things in, and they just need one little tiny transaction to fill the space. They're going to go grab whatever they can grab, including the ones that have no transaction fee on it. But if you reliably right now want something to be done in 10 minutes, you have to have at least equivalent of 8 US cents as of a couple months ago. That might have changed recently with the tests last week. I don't know what the newest is, but when I asked about a month ago, if you wanted reliably to have something be committed in 10 minutes, you needed to put at least 8 cents on it.
Is it reliable because not a whole lot of people are using it, or why is it more reliable than the non-transaction?
That every miner wants that 8 cents and will prioritize your block such that they'll put it in there. Whereas if it's 7 cents, 6 cents, whatever, it may be 20 minutes. If it's 0, it might be a day or a couple of days before, it's kind of floating out there as unconfirmed. And, until some miner basically wins a block that included that transaction. So, that can be a while.
So, coming to your point that the miners, if they come to a consensus somehow to reorder the blocks based on their profit margins.
Well, it's not reordering the blocks,
Blocks.
but the transactions within the block.
And if I'm running a full node, will that impact me?
Okay, so the question is if reordering blocks would impact a full node.
Right.
So what Chris is talking about is while the miners are trying to solve that puzzle, the proof of work, the Tetris puzzle, if you will, is basically hashing the data structure contained within the block. What's inside the block is the transactions and then the nonce.
So block order is not changed, but
The transactions within get changed. So by just changing one bit changes the hash tremendously. And so...
and the full node will download the blocks.
Well, so the first priority for a full node is to broadly gossip about all the transactions that have not been, secured at this particular point. Okay, so it's basically gossiping to everybody. Hey, there's this transaction that's not in a block, and it's spitting it around all over the place, and it's hoping the whole world has a copy of that transaction. The next thing it does is it looks and goes, oh, has somebody won a block? And if it has, it then adds it to its list. But it doesn't actually, they don't actually, what are the final blocks? That's what the miners do.
So,
No.
last question. So, if the transaction fee is there to prevent a denial of service attack, but you don't have to pay a transaction fee, why doesn't anybody who wants to attack using that just not pay transaction fee? I don't understand that.
So the question is, well, if you don't have to pay a transaction fee, and if the transaction fee was there to prevent a denial of service attack or something similar to that, why haven't you done it, a denial of service using that vector? And I would say that until it becomes a problem, then there would be a reason to modify and do a hard fork as to enforcing that. So right now, who's enforcing the rules are the relays, the nodes, the miners. And right now, the software out there permits transactions without a fee. But should that attack occur, I'm sure that a fork of the software would require a fee at all times. But right now, yeah. So there just hasn't been that case. Yes?
Sorry, so on this line, are there situations where there are transactions with no fees that don't get confirmed at all? Like a lot of them, they're out there. I thought I remembered reading that pretty early on in the network, there was a whole bunch of transactions that weren't confirmed because of this.
So yeah, so the question is, well, if you don't have a fee and it doesn't get confirmed, what happens to it?
Yeah.
So yeah, so if you have a transaction without a fee, you really are up to the luck of the draw whether or not you get in. And it looks like from the last stress test, I think it took up to 3 hours for a transaction without a fee to get in. Now, but what if it doesn't get in? It just lingers forever in the mempool. And the answer is actually no. Eventually, it will clear itself out and dump anything that hasn't been put into a block after a certain amount of time. As to the rules, it just depends on the implementation. So it will eventually get kicked back to you, but you could be waiting quite a while. So yeah, you probably don't want to do that. All right, and then, all right, I think we talked about all this. I mean, and then the difference between your transaction and your change is the network is a fee. So let's talk about the standard transaction types. There are of which there are only these 5 currently. And so we'll talk about each one. The pay to public key hash, pay to public key, which is depreciated, not used as much. Multi-signature, which everyone's doing. And I think that's probably the most secure and safest one because, again, it's much easier to lose control of your Bitcoin due to loss of the passphrase or key than anything else. So if you have multiple keys, hopefully you can find a couple to unlock it. Data output's an exciting new one. This will be the op return, the null modem, op return. We'll talk about that later. And then pay-to script hash, which is an interesting transaction type when paired with multi-sig. So this one is the majority. When you talk about Bitcoin transactions, people are most definitely probably thinking about this one. This is where Alice and Bob are interacting, sending value between two parties. So this is where we're transferring value from one participant to another participant on the network. And they have the following constructed form: a script sig, or the unlocking script, followed by the locking script. Now, you'll see later, probably when talking about scripts, why this order makes sense. Because right now, it kind of looks like it's backwards. You go, well, when you have the scripts ordered differently. And this is a direct result of the fact that we're using a stack-based language. So. But yeah, so, and this is a little bit outside the scope of this talk, but we'll talk about when we talk about scripting. The reason why this pay to public key hash is, in effect, replace pay to public key, basically the idea being that we're hashing the public key. So that's why this one has been, if you will, no longer used as much. It's a smaller transaction, but the threat of, if for some future where we do have quantum computers, which again I really think that's far off. I mean, when you really talk about it, and oftentimes people confuse what they mean by quantum computers. If you're talking about wave functions or qubits, I mean they're very different. I mean ideas, which again, but theoretically, if a space alien were to land and had one, I mean, you could theoretically back out your private key. Whereas if you hash it, even if the curve were compromised, well then the key is using a different math, and you could still be okay, and vice versa. So this one, just again, it's bad practice to use this one. It's not used as much. Multi-signature, this is one that has everyone interested. This is the one that I think everyone should use. In fact, I think that when you see the power of this one, it becomes very obvious why you'd want to do it. This is an M of n schema where you have, if you will, a total number of n keys. Now, you're limited to only 15 keys currently, again. So you can't have, let's say, 100, but you could have 15 keys sent out to 15 different people or different places. And you could designate how many you need of that set in order to unlock it. So where you'll see this, I think, in the financial side of the house, is where perhaps you have a business system or workflow where you have multiple people that need to sign off on a transaction, or an encumbrance, or a purchase order, or whatnot, where you could have this built right into the actual workflow of the business. You see this with Copay. That's a great site from BitCore. So Copay is their take on multi-sig wallets, where you could set up multiple parties all having to sign off, or a minimum set having to sign off before the transaction is then pushed out to the network. So you could automate that. Yes?
Question. So the outputs which we talked about yesterday, right? And there was a conversation about opt verify and signature.
Yes. So
and will it have a structure of the multi-sig, multiple signature verification?
So the question is, well, when you're constructing, if you will, the scripts, how do you construct it with a multi-sig? So to answer that, it's beyond the scope of this talk. You'll see it in the next talk when Matthew talks about it, and he'll go into much more detail about the actual scripting language. But yeah, you have to build this up prior to use. So you basically create the multi-sig address with however many keys you want to use, and then you generate that script, and then you can deploy it.
So output 0 and output 1.
So then the unlocking of it will require a combination of keys such that they can form, and it's a little bit, until you talk about Merkle trees and whatnot, Because how can you know whether or not those keys are within that data structure? It has to do with hashing Merkle tree. So if you have the multiple keys within and you hash that to make a smaller value string or number string or whatever, yeah.
Since there are a couple of people that are working on Ethereum or other advanced things, this multi-signature thing has some huge opportunities, both in the Bitcoin version of the hash chain, but there are also, when we use other curves, in particular the Eris and some of the newer blockchains, there's some real power in additional capabilities that are here. So, I mean, among other things, you're not limited to 15. In this one, they all have to be presented in order, which is sort of a kind of a privacy issue. You can know who, with this version, you kind of know who signed it. You know, it was keys 5, 7, 9, and 12. Whereas in some of the other schemes, you can actually present it that it was you know, somebody, it was authorized, but won't tell you who among the different people authorized it, which adds for anonymity. So there's a huge amount of power in this multi-signature area that even now is not done.
And the wallets right now
Yes.
have the capability to do
Not all, but that's was where they're all trying to. I mean, literally, like we've been suggesting people do Bitcore for JavaScript, and the first Bitcore client-only JavaScript wallet that does multi-signature only came out like a week ago. So, what's that? I can tell you in a second.
So yeah, we'll actually look at Copay, I think. I think that's a great implementation. Also by BitPay, part of their suite of software that they have. And also, if you're using Bitcore, you should use their Insight broadcast. That's a great tool as well.
we talk about organizations, right? And the situation where the approval process happens.
Yes.
So you, the boss, your boss, the boss.
Yes.
Hierarchy comes into place, right?
Yes.
Can that be said that, you know what, this person can't sign before this person does?
Well, that is a great question. I think that the protocol doesn't have that kind of behavior currently in it, but you could write software that would allow that. So the question is, can you have within the protocol, the transaction, the sequence of sign-offs built in? And the answer is no, not currently. But your business system, well, I mean, they don't trust the person. They shouldn't even have the key to sign in the first place.
You might be able to do it with a combination of pay-to-script hash and multi-signature.
So, yeah, so what you could do then, of course, is then start building on top of that your own internal structure and add that functionality using these other tools. So that, though, is not a standard transaction type. So, but yeah, you can definitely play with the various standard transaction types to get what you want. This one, I think, is probably the most interesting of all the transaction types, and that's the op return. This is how you can put data within the blockchain. And in fact, this is really the whole allure of the blockchain is to do just that. It's an immutable shared database, holographically created database that every node has a complete copy of. Every full node, I should say. So I think that this opens up many possibilities. The reason why that this is so interesting and why it was added as a standard standard transaction type was prior to this, people were putting data into the blockchain through non-standard transactions. You can put a non-standard transaction into the blockchain. Luke Jr.'s mining pool, I can never pronounce it.
Yeah, I don't know.
If you send, and that's how they have photographs. They have, I think they have book of poems.
I'm sorry, it's just like
they have, I think they have the entire works of Shakespeare. How did they get that into the blockchain? And why is it that you have now a copy of that on your local copy? Well, it's because of people putting data into it in these non-standard ways. So they want to effectively make a standard way that would still allow people to do this, to have this functionality, but do it in a controlled manner. So
another aspect of it is when people were doing these tricky things to do things like they would create addresses that had no private keys associated with them, etc. That also meant that every time you were trying to validate those blocks or walk through the history to validate those blocks, you'd have to do these calcs that are meaningless, because it's like, why are you validating when it's not anything useful? So you're spending all this processing power to validate things. Everything past an op return isn't validated. So basically, it's just saying, you can skip the rest. You don't have to do any processing on the rest. So it had a real impact on processing.
So, yeah.
But just to be clear, isn't that the activities of the miner, right?
Right.
This is just you're not building that.
This is the transactions.
And then another comment might be I think that's considered sometimes when people are trying to figure out ways to attack the network, like putting unessential things in op returns and doing, like you said, not including public keys in that, as well as potentially putting even a virus in an op return that could be there that someone can maybe be infected by it at a later point. I don't know.
So yeah, there's definitely some, issues. And again, what Chris said was absolutely true. I mean, people were doing that. I know I did that even. I mean, with CoinGroup, they were. And it was just basically unspent transaction outputs must be always accounted for. So they're always within, if you will, the mempool. But if they go to a fake address, it just means it has to be carried over forever. Whereas once you spend that unspent transaction output, and that can be written to the blockchain onto, if you will, hard drive, long-term storage, and taken out of the memory. So
spent transactions.
Yeah. So once you take that unspent transaction output and then spend it somewhere, that prior transaction can be written to the blockchain and basically taken from RAM to hard drive.
So I mean, you can think about it: the $3 billion of the current unspent transactions all has to be kept fairly quick in a node, so that the node can say, wait a second, that's been double spent, because that's what you're trying to avoid. So it keeps all those types of things in a much faster access. Whereas past transactions, things where money has been spent, these op returns or whatever, you don't need, you're less worried about double spending because there's nothing to double spend. So it's trying to prioritize these unspent. So if you put $1 on an address that's a hack, that is because there is no private key on it, then it's got to keep that around forever.
Although there is value, and I'm thinking that like the counterparty funding is going to prove the firm, right? I mean, there is value in that, in the ability to spend to an unspendable address.
But a lot of tears were shed that day. That was perhaps one way to deal with it. It's very, the proof, well, whatever.
Question, so are people using this operator and standardized data and attaching a transaction with various
in fact,
documents?
and this is the one that I think I'm going to spend the most time on, and we're going to actually see this in action, because this is, I think, what my bias, of course, the whole point of this class is to make use of this, because now you have access to this ideal database. It's immutable, it's timestamped, it's global. It allows for services that are just mind-boggling, notary services that are par none. So it's really quite interesting. So we'll actually look at this. We'll look at the op return. We'll see how some transactions, you don't have to have in your transaction just one of these. You can have multiples of these. You could have a transaction that you broadcast, that you pay somebody, that you have an op return, 2 op returns, etc. You can have multiple of these within your individual transaction.
I mean, in mine, I'm putting the signature of your SSL certificate in there. So I'm not putting the whole certificate, just the hash of it. And these are designed to put hashes in. Like I think it's actually been very deliberate. The reason why it's 40 and not like 120 or something like that is they wanted it to be small enough to put hashes in, but not big enough that you're putting, you know, entire transaction numbers or you know, full signatures or things of that nature.
And in the case of one of your projects, microwork, right? So you can generally say, this is, if you do this documentation, I'm going to pay you this much.
Yes.
And this is the standard I have. And you send it to someone, they can attach it, and it can match, right?
With regard to microwork.io, that's a smart contract, and that's based on, I believe, not Ethereum. I think they're using Codius, and so it's within Codius's. So yeah, but we'll talk about this one in detail. It's going to go to 80 bytes hopefully soon when everyone upgrades to 0.10. Who knows? But right now you got 40 bytes. Yeah, it's kind of limited, and it's also done in such a way that's prunable within the blockchain. So again, if you have an unspent transaction output that has an op return, you can delete the op return. It's just a null return. Just like in any programming language, it's just a return operator. And then again, the last one, pay to script hash. So in a multi-sig situation, you don't want to, for example, it might be cumbersome for me to pay an address in a multi-sig whereby it just leads to a very large, cumbersome transaction. Well, I could pay to a hash of the script that will unlock those encumbered funds. So it's basically a way to make for a smaller transaction. All these standard transaction types, I think, are really elegantly described in detail in Andres Antonopoulos' book, Mastering Bitcoin. And honestly, that is definitely a tool. I think everyone should you can get a copy on GitHub. Personally, I got a book myself because I like to write in it, but the GitHub will get you up and running very quickly. And we're going to use some of their his vernacular with regard to explaining this. So here, let's talk about how a transaction looks like and how I approach it. So we're going to see about building a transaction today. And I remember when I built my first one, it comes to you looking like this. This is all handled behind the scenes in your wallet software, right? You don't see any of this. But if you roll your own, this is what you're going to see. You're going to see this serialized hex string. And you got to know, well, what do all these numbers mean? Or what do all these things, these objects mean? And this is something that we're not going to talk too much about because Ryan X. Charles is going to go into gross detail about each one of these data structures, which is wonderful. I mean, it's mind expanding when you really get down to it and talk about the idea of little Indian versus big Indian versus all sorts of crazy stuff. I mean, the one thing though that I had the hard time was you got to remember everything's hex. So you got to convert everything either. And you got to know which one you're going to, of course. If you're going hex to binary or hex to decimal, you gotta know how to do that. We'll see some tools that I'll share with how to do that conversion on the fly, so you don't have to do this yourself. But briefly, what I just did is after looking at it, started delving into various, Andre's book, the wiki, etc. And I realized that not every single one of these sources had a complete understanding of what every single one of these, they would just wrap them and say, well, it's a signature. Well, what are the individual components of this? So, here version number 4 bytes. Here's the input counter. How many inputs are we talking about? This one just has 1, of course. This is, again, the input, the transaction input. This is, if you will, the hash transposed of where the value is coming in from, all this. Anyways, this is a little bit more easy to see. So how about we go look at it real quick just to get a general sense of it. I put this up on a blog. We can just do a quick, you can't see that, so hold on me.
Jeff, is it on Slack?
And it is on Slack, but I'm going to put it on Slack, show mirroring, arrangement, mirror displays. Okay, let's take a look. Oh, come All right, boom, bada boom. This is not at all what I want. All right, so here we go. So this is a simple pay to public key hash. This is a, if you will, the simplest transaction type. It's just going from one person to another person. And it is, I'm having all sorts of technical problems with the thing. All right, so here it is. This is where we're going to send money from the payer, and here's the address. You can see what it looks like on Chain's Block Explorer. We can see that it's now empty, of course. We're going to move this initial value from this address to another address. We're going to spend 1 million Satoshis. Here is the unspent transaction output. You have to get this, of course, you have to get this, of course, from a Block Explorer. If we look in the raw data. So we're going to have to look within the raw. Oh my goodness, it changed the resolution on here too. It's hard to see everything. Where's the outputs? I can't read that. We'll look on it after I figure out what's going on here. You obtain this information from your Block Explorer, which will tell you where it's located. This is a transaction hash. So this is only after it's gotten into a block that you know this information. So one thing you have to be aware of course, is when you're putting this in, you have to wait until it gets into a confirmed block. It'll give you a temporary transaction hash, which might or might not change. So that takes a while. Oh, I'm sorry, this is... Oh my goodness. I have no idea why it's doing this. All right, let's just, and I'll put this up on Slack so you can take a look at it. Here's the public key, here's the private key, which will generate, hopefully I'll figure out what's going on so I don't have this problem. It's driving me crazy. This is where we're going to, let's do a go to. That could have been dangerous to go here, but we see that here's the value that we've added to it. So here's where that million Satoshis finally went into. So we did in fact move it over. So this is, again, the version type, this is the number of inputs. Oh boy, I shouldn't have done that.
Someone scroll down.
It's just something is weird. Once I, oh, okay, there we go. Everything got reversed here. I like it a certain way. I'm a creature of habit. And then here we go. So here's the previous transaction output hash in little Indian format. What's that mean? It's just transposed for us. This is, in effect, what that means. So when we talk about that later, you'll see. You get this, of course, from a Block Explorer like chain.so or blockchain.info or blockcycle, etc.
And the WIF stands for wallet information format?
Yes, wallet import format.
Quick question on this. So what's the bit where the miners actually picked it up and does a nonce and hash it over and over again 10 times? So in this, which part of it they do?
So what your question is, when the actual transaction is put into a block by the miner?
Right.
When is this created?
Oh, what I was trying to get is when they solve the puzzle where they do them.
And they have the nonce and incrementing that to
Yes.
try to get to
Yes.
a hash that has the requisite number of zeros in front.
Right, right.
Well, what's interesting is that transactions and blocks are almost separate entities.
Okay.
And they have a lot tied to one another, but in fact we can compartmentalize them and think of them as separate. So when we're talking about transactions, these are inside of blocks, and we need to know where they are to find them inside the blocks. But that's a separate idea.
Okay.
It's a different PowerPoint even.
You can kind of think in the Tetris sense, this is one of those little things.
Right.
Some of them are large, some of them are small. Nodes care about them, but it's the miners who are trying to do things with them. But until a miner's done with its puzzle and it's won, you're not things can change.
So this.
But that transaction there's from an old block. That's not from the current block. That's not the transaction for this
Right.
thing.
That's right.
It's from something that happened successfully in the past.
Yes.
But I think if I understand Deepak's question correctly, this whole stream of hex is what's included for this particular transaction in the block that it was included in.
So that's not only unlocked and this is the output.
Can you just grab that hex value and go to the Explorer and show where
Cast, if I can spell. You could literally write. That's what I want. You could literally write your own on a napkin, and then copy it here, and hit send, and it will then push it out to the network. And provided that it's a valid transaction type, and this node accepts it as a standard type, it will say, I'm free to broadcast that to all the nodes I have contact with. Those nodes will pick it up and say, yes, it's valid, and then they broadcast, and it just gets pushed out throughout the entire network and promulgated throughout. So yeah, I mean, you could just write your own, if you so, I don't know, that'd be, you probably should go to Vegas first, if you could do that. There's probably more value, but yeah, it's really quite interesting. This is in effect what a transaction is. In fact, you know what, I wonder if I just hit copy, it should say, hey, this has already been spent, but, oh, it already translated it. Look at that. It just, that's
I
new.
didn't know it did that.
It didn't. So it just translated that on the fly. So here we go, version number.
That's from your notation, isn't it?
I'm sorry?
Is that because you copied your notation?
Oh, that could have been it.
Yeah.
That'd be cool if it did.
Yeah.
Because it's written the way you wrote it.
Oh,
That's cool.
ignore that. It's not that cool. Never
You
mind.
copied-
You're right.
Yeah.
I was thinking, oh, it just copies the value. Oh, let's go through it real quick, and then we'll take a break, and we'll look at tools to decipher this and actually build up our own transaction.
Will all this be on the test, by the way?
Oh, yeah.
Actually, can I quickly, so it is unlikely that you will really need to know down to this level of detail unless you're doing really fancy things with, in the future with Bitcoin. Basically, you're going to rely on your libraries and all that kind of stuff to create these things. The reason why we're demonstrating this isn't so much so that you become an expert at it, but more of so that you have this kind of a sort of a basic familiarity of, oh, there's some interesting complexity that's going down there, and it's possible if I need that in the future. And then some of these concepts kind of might help with things you will want to do in the future. So.
Yeah, it's really, again, what Chris is saying is absolutely true. All of this can be handled using tools and libraries that pre-exist. In fact, you would be foolish to do this yourself at this point, because more than likely you're going to make a mistake. Whereas using these tools properly, it's all been vetted. But again, it gives you an appreciation to know what it's doing. There's no magic. It's all predefined. The data structure is well defined. Everything must conform to this kind of a structure. One thing that that is kind of interesting is, because it's a stack-based language, you have to tell the computer, the stack, how much data is going to be pushed onto it at any one time. So every now and then you'll see numbers that just, you don't understand why they're there. It's really just to tell the computer, hey, push 47 bytes onto the stack to do something with it. What are those 47 bytes? Well, it is the signature. And so this is what's happening behind the scenes. It's a very dumb computer, really. It's very simple to understand, it particularly if you like reverse Polish notation. If you ever have an HP calculator, you know it's the best way to do it. And that's really what we'll see later in a different...
For us old-timers, it's kind of like fourth.
It's fourth, yes. It's a fourth-based language. So, again, pushing, the public key is pushed, and then etc. Here's the value finally. We are on the value right here. So, and then this here is the script that, in effect, encumbers or locks it. And then here's size in bytes of the locking script. We duplicate. Remember how we saw op redupe, op hash, push data. Well, that was ignored. and then the hash of the destination public key. So here is that script inside of this transaction.
Hash
Well,
of
the
that
hash,
same public
hash
key.
160 was there, right?
Yes.
That-
Yeah, right here, yes. So we're doing a op hash 160, so ripe MD 160.
Okay.
This, however, as I recall, Chris, correct me if I'm wrong, this is actually doing the SHA-256, SHA-256, ripe MD 160 base,
All ones, yeah.
base 58, so it's kind of a misnomer.
Yeah, that's what SHA-156 and RIPE-MD.
And then base 58.
Base 58.
Yeah.
Okay.
All right. And here's some resources. I'll post this up on Slack. We can see, you know, we'll actually go and use our terminal. We'll make a transaction, or rather we'll build an address. We'll then fund that address, and then we'll create another address and then transfer that from one place to another, all within the terminal. So, are there any questions? Yes?
How many outputs can you have in a transaction?
You know what? That's a great question. I forget. I think it's
Not
well, first
larger
off,
than a block.
size requirement, and it's also, is it 49 that there's a, well, first off, it has to be within the size of the block. You can't have a transaction that exceeds the size, and the blocks are currently limited. It was always thought to be 1 megabyte. It looks like it's,
Would they do a block with just your
3/4.
one transaction? Because
there are
it's-
blocks with no transactions, or it's just dummy information. So some miners, in an effort to try to win the block fast, will just start working on the hashing and have empty blocks. So that's a faux pas. But yeah, transaction, I believe, is limited to 49 or some number in addition to the size. So you can't have
I think- And I also think that it's like some miners, I think it's not a hard limit, I think
Yeah.
it's a soft limit, so like some, you know, by convention, most miners, and I think it is like, 50,
Yeah.
will limit it to that, but there are some miners out there
Yeah.
who accept all kinds of things.
Yeah, so again, Luke Jr. is famous for his pool, will accept anything. So if you have a non-standard weird transaction of weird size, send it over there and it gets in, you're lucky. You're right. So,
Like the opposite of that, how many inputs can you have?
again, you want to minimize the total number to keep the size under a certain
Okay.
extent, so that you minimize your fee that you're to pay, because your fee is based upon, if you will, the size of the transaction, the standard transaction fee, I should say. So if you have a larger transaction, that means a larger fee potentially.
Okay.
Why do you have little endian and big endian mixed up? I still don't understand that
Oh,
concept.
you know what? And that's perfect. The question is, what's little and big Indian? And
No,
that's
not what. I mean, why is it mixed up? Why can't we just have one endian? That's what usually
Oh.
systems have, right? I know what little endian and big endian. Why is it?
oh,
mixed
I
up?
don't want to steal any thunder from the next talk, which is going to be brilliant. So I can't say anything. Just keep. That's a good question, and you're going to see. It's quite amazing. In fact, it's really quite amazing. Oops. So we'll take a break, and then what we'll do is we'll